Well, it's official. Welcome back, folks. Well, for our first day back on spring break, I'm not going to try to do a whole bunch of stuff as fast as possible. Kind of what we're going to be doing is just getting recall what we were doing prior, look ahead in the schedule, see what we're getting into, and we should be getting through section 4.2. If we have enough time, we'll take a look at section 4.3, but I don't want to get too deep in there. It's mostly just posted in case we have a whole lot of extra time towards the end of class. But welcome back, everyone. I know spring break is sometimes a little bit tough to get back into linear algebra, especially in this part of the course, which is a little bit tricky. So any questions at all, folks, before we get started today, either on the upcoming assignment 15 or what we're working on currently? Okay, well, aside from the other announcements, we're pretty much just started on section 4.2. We're only on the second example. And what's coming next is in section 4.3 and 4.4, we're going to have some updates to the invertible matrix theorem. I put all of them into this overall document right here. So this is our next invertible matrix theorem. It has everything you'd want from chapter 4 already included. And it's pretty much probably your expectation as well. That's going to be one theorem that will be provided on exam 3. So good to take a look at it sooner than later to kind of just get yourself acquainted with the new elements. In fact, let's take a look ourselves. Here's the brand new theorem. I still have the determinants not equal to 0 on the very, very bottom, since that's usually how people like to organize this, the determinant relating the invertible matrix. But all these are logically equivalent. And the new things we're going to be taking a look at is, well, we've already dealt with the null space, and the null space containing just the 0 vector means you only have a trivial solution. And if you only have the trivial solution, that would mean the columns of that matrix must have been linearly independent. And then we're relating really every single statement here. I'm just grabbing the more useful or interesting ones. And that tells us we have an invertible matrix. So if there is essentially only one element in your null space, the 0 vector itself, your matrix had to have been invertible, is what all this is saying. These are new statements we're going to take a look at. Dim will stand for dimension. And so we're getting very close to actually finally defining dimension. So that'll be exciting once we cross that bridge. But that'll be our new theorem. So this one will be included on the upcoming exam 3. And let's take a look at when that is. I'm not honestly too sure. It's been a long break. Our exam 3 is Tuesday, April 15th. And that's going to be about, let's see, looks like that's a typo already. That should have said April 16th. Let me get to the notepad here and I'll correct that later. Exam 3, we're not a Monday class, we're a Tuesday class, will be April 16th. But that one is going to be 3 weeks away, so we still have a good amount of time before we get to that one. I'm going to try to post information a little bit earlier on this because the exam 3 done, we'll have a normal week here. This will be a normal week on Tuesday, a review day on Thursday. And, oh, hang on, let me take another look. No, that's finals week. After we're done with exam 3, we go into a half week where 1 week will be new course material and the next day will be just reviewing for the final exam. So I'll try to post information here a little bit sooner since we're getting pretty close to finishing up the course. Well, just 5 more weeks to go at least. Well, any other questions or comments, folks, about what we've got going on so far? Okay, well, let's take a look at where we left off. We left off here on example 2, but before chewing through this, let's pause right here where it says the null space. We're concerned about null spaces of any size matrix, so it doesn't have to be square for this definition. And just to get a warm up for today's class, let's just write down that definition. Null A is going to be the set of all vectors X in, let's take a look. It has to do with that n by n matrix A. So if we're dealing with that size of the matrix, then the vector X will multiply, and it has to be of size n by 1 in order for the multiplication to really actually work. So that tells us our vectors X has to have n entries altogether. So from that statement, we'll say X in Rn. This portion here isn't completely required, but sometimes a good idea to say specifically which vectors X, right in this location, because it'll help us to determine what subspace we're even dealing with. Looks like it's a subspace of Rn. So this n right here, let me see if I can add a little bit of space to properly point to it. That n right there, let's try that one more time. That was supposed to be an arrow. This n right here, I feel like I got rusty on the digital pen over the break, is the same as the n you see right here in defining the null space. All we have to do is take that matrix A, multiply A by X, and the result has to be the zero vector. But this is also kind of confusing in a way. This zero vector right here is not a zero vector in Rn. This is going to come into the codomain, which is that dimension right there. So if we multiply A by X, you will have a resulting size m by 1. That means that zero vector over here is of size n by 1. Oh, I almost got it. M by 1, there we go. Well, that's what our null space looks like. In other words, we're just looking at all the solutions to the homogeneous equation right here, and we collect them in a set of all those x's. It has to contain the trivial solution, because putting in a zero vector here makes the equation true. Well, let's go back to the theorem. The theorem tells us right out of the gate, the null space is automatically a subspace of Rn. And again, that n shows up right here due to this n as well. This is probably one of the more, I'm tempted to say, most important subspace that we'll study in this course. It'll be used quite a lot in chapter 5 to define eigenvalues and eigenvectors, which is a massive application to linear algebra. And so we'll have quite a lot to say about null spaces, starting really today, I'd say. Here's the first fact. This is labeled as a corollary, meaning it's a direct consequence to the theorem right above. The null space is a subspace. Then we can say the set of all solutions to a homogeneous system of m equations and n variables, that also has to be a subspace. That's a direct consequence because all that's happening in that corollary is we're taking a system of equations, here it is, in matrix form, but it'll be the same system of equations if we write them all out in this form. So this would be the ordinary system of equations. And so pretty much all that's going on here with the definition is, for looking at the null space directly as a set like this, it's a subspace. But you could take that matrix form of the equation, and if it's truly homogeneous right here in our system of equations down in that set, then we can just use their corollary to answer the question down below for example 2. So example 2 says, let W be this really odd looking set. We wonder if it's a subspace of R4. And first look at this portion. There are 4 entries, which says the question is well formed. If they said, is it a subspace of R3? It's automatically a no. It doesn't even belong to R3 as a subset. So now to get through this problem, we'll direct our work at it just using the corollary. So let's see if we can really write down a homogeneous system of m equations and n variables. So take the set W. Let's rewrite it as PQ RS. Well, that's copying so far, but let's just rewrite at this stage. Right where the comma is, if we subtract 4s, we'll get P minus 3Q minus 4s equals 0. On this one, we can subtract maybe 2p from both sides to get negative 2p plus s plus 5r, also set to 0. And now the zeros here are extremely special. We have equals 0, equals 0, and that means we are looking at a homogeneous system in this problem. So our work is essentially done. We can now say, by the corollary to theorem 2, W is a subspace of R4. So it's a fast problem, but it's an extremely confusing problem. Watch out for these kinds of sets when you're doing the homework set for this section. Sometimes if you see a set that looks like this with just a vector indicated, you're probably doing this approach with the corollary we just used. Well, any questions, folks, on that first problem after the break? Okay, well, let's take another look. This is such an important theorem that I felt like we ought to try this problem next. I feel a little bit of guilt with this one because it's kind of a tough problem, but it could help with the homework that's coming due on Thursday when we're dealing with subspaces and such. So think of it, this next example, not something that I would ever ask on a real exam. That's kind of a tough problem. This is more just a review from section 4.1 and also to help out with the homework. So let's put a little bracket here. This is just a repeat of the theorem that the null space is a subspace of Rn, and let's actually prove it. If it was a homework question, this is the very first thing I would do. Let's look up some information. You can go to the blank lecture notes up here. Oh, that's somewhere over here. There they are. Go to the blank lecture notes and you can pull out the 4.1 notes without all the markings we put on it. Here it is right here, and just grab that definition. We'll work the problem directly, citing that technical definition there. Let's see if I can just rescale it just a touch. Okay, there we go. Well, any questions at all, folks, before we begin with example 3? Okay, well, we already know from what we did before, this null space of an n by n matrix A is definitely a subset of Rn. Let's rewrite that work again, just so that's visible on the notes right here. So for our first step, we'll write null A is a set of all vectors x. And it will be x's in Rn to make the multiplication work, such that A times x results in the zero vector. There's lots going on with this matrix equation right here. So let's first put in the size of it. A is m by n. X's came from Rn. That's required to make multiplication work. So x is of size n by 1. And this zero vector on the right-hand side, it's not a zero vector in Rn like we mentioned before. It's a zero vector in Rm instead. We can tell right here from the multiplication, the result of A times x will be of size m by 1. So that's the statement so far. Let me just extend that bracket a bit. And that's what we need to work on. We'll say this set here, first thing we have to do is, on our part A, let's go to this portion. We need to grab the zero vector of v. In this problem, v is going to be equal to Rn. So let's just grab that. Let's say let 0. It's tough to say which zero vector sometimes with these things, unless we put a subscript on it. We'll say n by 1, so that particular zero vector be the zero vector of Rn. Okay, so that's the Rn right here that we're trying to show it's a subspace of. Now we need to show that this is actually in the set for null A. How do we do that? Well, we need to find some way that this equation is true, but that's almost automatic, right? This equation right here always has the trivial solution. That'd be the zero vector you just throw right inside there. To tie off this statement, we can just say since A times that zero vector that we just defined, let's call this n by 1 just to be specific. And I feel like we should put a color on, well, I don't want to use too many colors. Since this is the zero vector of size m by 1, that's all that was required to get inside the set. We just had to take this thing put it right here and show that you really get the zero vector as a result, but we know that to be true when we multiply a matrix by a zero vector. Since we do get this result, we now get to say that zero vector is an H. So let's now say this shows the zero vector of size n by 1 is in null A. So the H in this problem is that null space. Well, any questions, folks, with that very first step with the zero vector? Okay, I honestly feel like this step is oftentimes, even when you get a lot of practice with subspaces and this definition, that's always the kind of more technical one, because you're looking at a zero vector from one space, showing it's inside H, but to show that you have to use set theory where there's other zero vectors you have to consider all at the same time. So it's a lot to untangle with these kind of problems. But again, think of this as a review of the subspace definition, which is massively important in linear algebra and also really confusing. It takes a lot of practice to get a feel for it. The next parts, B and C, I don't think they're as tough. And here's how we can start them off. We need a couple things, vectors UV, and we need a scalar C. So I'm going to just start off by defining all those things all at once. So my U, V, and C will be in scope of both parts B and C. Let's write out that statement. Let, starting right here, H is the null space of A, so we'll say let U, V, be in null A. And let C be in R. So now we've got our vectors, we have our arbitrary scalar C. The next thing we have to show is this portion. We want to know if that linear combination, just the vector addition of U plus V, if it's really an H. To do that, we have to do the set theory on this thing. This is the set membership condition. But even before that, what we should really do to start off is the moment you said U and V is in the null space of A, we should write down what that means just immediately. Let's say this means so let's take a really fast look. U is in null A, means the vector that goes here, it comes into this location, and it just means A times the vector U results in a zero vector. And likewise, A times the vector B also results in a zero vector. So that's once again coming from right here. Now that we have that, we can get back to this step. We have to show that vector addition, U plus V, is still an H. That's not too bad any longer. We can now say, let's scroll just a touch here, since, actually, let me move this thing. There we go. Since, well, again, we don't necessarily want to write down U plus V out in the open and do something on it. Because if we're trying to show that U plus V is inside this set, then U plus V really goes there. That's how we're going to show it's really inside the set to begin with. So let's write, since A times the sum U plus V equals, and then go from there at this stage. Now we have to do some matrix algebra on this thing. And one matrix algebra statement that we used in chapter 1, we used it for linearity as well, is that A will distribute across a sum. I believe this is a theorem in section 1.5. When A distributes across a sum, you get A times U plus A times V. By that stage, the prior statements take over. A times U, we already know to be the zero vector. Likewise, A times V is also the zero vector. It's a zero vector in Rn, and certainly adding two zero vectors give you back the zero vector. And this is what we need to show, that we got to that zero vector right there. Since we showed it, we can say, this means, let's say, since we have the zero vector right here, U plus V is in H. So that's the statement right here that we were going for. And I forgot to write down, this is the part B portion. Let's just put it right here. Why not? We're almost done. We just have to show that this property is going to hold C times U is an H. But it's going to go essentially the same kind of way. We start off by putting C times U right here and just multiply and see what happens. So let's run through it. We'll say since A times CU, now that CU is playing the role of the X that's right here. We need to hit this zero vector. So let's do some algebra to see if it works out. So the same theorem from section 1.5 that we use again on linearity also tells us down here that in this configuration, you can reassociate. The scalar C can commute in front, and you could just take A times U, associating that matrix multiplication. But the moment we do that, we go here. U was inside the null space. That means A times U is the zero vector. So this is C times a zero vector. Another property about vector spaces is if you rescale the zero vector, nothing ever happens. It stays as a zero vector. And that is enough to show C times U is an H. So that's the last portion right here. We checked off every single part of the subspace definition. So really all we have to say is one overall conclusion. This shows null A is a subspace of Rn. We did it, folks. I think that one is kind of a tricky one to get through. Any questions about any one of those steps that folks would like to discuss? Okay, kind of a tough one right after the spring break. Sorry about that. Weird timing on some of these topics. But let's take a look at what else we can do with these ideas so far. So this section is all about null spaces and another concept of column spaces. And here's our definition for what we mean by a column space. Now, as you look at the column space definition, one thing that comes back to us is going to be this theorem. Out of nowhere, it just makes a really big comeback. This is the one statement of logical equivalence where your matrix did not have to be squared. So we allow for an n by n matrix. So anything dealing with column space, it really is a theorem 4 of chapter 1 type of problem at its heart, which is kind of interesting. Getting back to this definition, here's how the column space goes. We'll have another n by n matrix A, and the column space, I'll typically just write by saying COLA for column space A. Oftentimes I'll put a parenthesis around the A, reminding me of function notation. That's more of a stylistic choice. What it is the set of all linear combinations of the columns of A. But if you take a look at the set of all linear combinations, that's just another way to say span. The columns of A go A1, AN. So the column space of A is just the span of all the columns of that original matrix A. AI is going to be the ith column of A. Let's say a little bit about that ith column. If A is of size m by n, that means there's going to be n columns, but every column will have m entries altogether. So over here, when it says A1, A2, AN, AI is going to just be any one of those different columns, but we can also say AI is in Rm this time. So that m, this time the first dimension you see, is what we're dealing with if we're working on a column space. If we're working on a null space, it would be a subspace of Rn, that second dimension you see there instead. So column space, because we're spanning columns with m entries, looks like it's going to be a subspace of Rm. And it turns out that is true. Well, any questions, folks, about column space? Okay, again, column space is just another way to say span a bunch of vectors. But usually you think of column space when you're working on matrix specifically. You're just now spanning its columns. This theorem here turns out to be really pretty important. So just like we proved the null space theorem, we'll prove this one as well. And it's a very interesting proof. You'll notice I didn't put in a lot of space here. That's for a really good reason. Anyone happen to know what the proof would be for this theorem? No worries if you haven't. It's been a long vacation. Well, one thing you can try is, it turns out the trick to the proof on this one is right here. We spanned a bunch of stuff, and we're spanning vectors that belong to Rm. So the M here is also important. But if we go back to section 4.1, just for a brief moment, in section 4.1, we have a really powerful theorem. And it's this one right here. It says if you take a list of vectors from a vector space, any list of vectors whatsoever, then the span of those vectors is automatically a subspace, no matter what. So theorem one takes over on this, and all we have to do is say, back to the problem, since the column space of A is the span of vectors in Rm, this would be the V in that theorem one, the larger space. We're spanning vectors in Rm. We can now say, by theorem one, this gets a little bit annoying in our textbook, just a heads up. I can't just say theorem one because there's a bunch of theorem ones. I have to be more specific. Theorem one of chapter 4. So I'll always put that in just to say which theorem one. So by theorem one of chapter 4, call A is a subspace of Rm. Again, the whole key to that proof is right here. If you span vectors, you automatically have a subspace by this theorem one. Well, any questions, folks, with that really rapid proof this time? Okay, it's kind of the best all-time argument in linear algebra whenever something is basically a one-sentence verification. But let's go back to the column space and focus on this part right here. The column space is the span of A1, A2, AN, where those are the actual columns of your original matrix A. So this question on example 5 is a little bit weird. It feels like it goes backwards. I guess it kind of does in a sense, because it says, find the matrix A such that it would have the property, its column space is that set right there. So let's see how to work through this. Pretty much the whole point of this example is just to get a feel for this definition when we say column space. But really, this could have been a problem we did in chapter 1. All we would do is take this and break it up. We want to undo the vector additions, undo the scalar multiplication, put it in a parametric vector format, essentially. So let's write out call A is going to be equal to, next thing we do is pull coefficients, and for the A coefficient, the first parameter there, we have a -1, 1, and 3. Then go up to the B coefficient, do the same. This is now 2, -2, -6. And just to be specific, I'll just say, as before, AB, R in R, so arbitrary scalars or parameters. So all I've done is taken this vector right here and broke it up. Now it's a linear combination. But that's what's being mentioned right up here when it says, let me take these off so it doesn't get too busy. Column space of A is the set of all linear combinations. This is all linear combinations, because we allowed A and B to be any value that is an R. So we have that part of the definition down. But the moment you say all linear combinations, That's all the span is, the set of all linear combinations. So let's take an extra step to just write it now as a span. This is call space A equals now the span of -1, 1, 3, 2, -2, -6. And notice when we go to write the span, we take off the A, there's no pluses, we just say which columns are you using, what are the constant vectors coming from here in all of your linear combinations. Now that we have that, we'll go over here to this part of the definition where it says you can get to here, the span of a set of vectors, you take those same exact vectors and form your matrix A out of them. So our problem is essentially complete. We can now say, once we get to this step, this shows A equals, and this is our last step, so let's slap it with some color coding for our final step here. We'll put in -1, 1, 3, 2, -2, -6. And that's our work. That's the matrix A that we were looking for in this problem. Well, any questions, folks, with part A on this one? Okay, well, we did it. That's another one down. And once again, looking through all of this, it's all about just saying what the definition is trying to say. If the column space A is the span of those vectors, then A itself is just formed by taking those corresponding vectors and just throwing them in. Now, part B is the interesting question, in my opinion. It asks, is the column space of A R3? Well, that's a really interesting question. If the column space of A was equal to R3, that means you could always write stuff like this. AX equals B would be always consistent for every, let's underline that part, B in R3. So if the column space of A is R3, that's what this is saying. I feel like I should probably say that part. Let me put in above. If column space A equals R3, then, okay, now we have a real statement. Then you could always solve that equation. X equals B would always be a consistent system. Now we wonder, could that happen? Looking at the matrix A, any volunteers for a yes or no on this? Would column space A really be R3 or is it not R3?
I would say no,
I agree, absolutely. You know the reason what the reason would be why it would not be?
because A does not have three columns. It only has two.
Exactly. There's no way to get a pivot in every row, and that's pretty much the heart of it. Again, that's just what theorem 4 is saying. This question is really asking if the columns of A span all of Rm. That's just a rephrasing of that entire question right there. I think that's an important enough thing to just include right here on this statement. This is the same as call space A equals Rm. So that's kind of interesting. And to me, this is what makes linear algebra kind of challenging. There are a lot of different ways to say the same thing. Column space A equals R3. You could just say it this way. But then all these statements are logically equivalent. We could have said it this way. That's kind of what we were doing right here when we wrote that statement down. But to finalize this answer, we can say call space of A is not equal to R3, as you said, because A has only two columns. That's pretty much it. That does it for us. If we want to relate theorem 4, you might say this means there will not be a pivot in every row. So that's the end on this one. Any questions, folks, with dealing with the column space so far? Okay, so now we have two interesting subspaces. If you write down any matrix A, we now wonder, what is the column space? Can the column space span its entire space that it's a subspace of, like R3 in this example? And same issues with the null space. We wonder what's going on with the null space for that particular matrix. Now, tying all these kind of things together, let's take a look at both of them at once. So examples 6 and 7 are considering both null spaces, column spaces simultaneously. And here's our situation to start off. It says, assume that A is of size 4 by 2. It's an element of R 4 by 2. We want to know for what value K is null A a subspace of Rk, and for what value of J is column space of A a subspace of Rj. That's a lot to unpack, but we just started talking about column space. So let's write this out to start. If A is in R 4 by 2, this means A is 4 by 2. And so the column space of A is going to be equal to the span of the columns of A, which all have, well, the columns of A would have 4 entries in total. So for answering this kind of question, we already know that the column space is a subspace of that object, Rj, but what we just found is, for this location here, because we're spanning vectors with four entries, column space of A is a subspace of R4. In other words, J would have to be 4 in this problem. Does that make sense to folks on that subspace there? Okay, when handling both these things at once, a column space and a null space, I think sometimes it's easier to work with just the column space. We can fall back on what we're doing, just spanning things. And then once you've done that, you've taken care of that dimension there. The 4 is already resolved, and so you can say null space has got to be a subspace of R2. So let's write that down next. Next, null A is a subspace of R2. In other words, K would be 2 in this problem. So we did it, folks. Again, this one is kind of just a wrap-up kind of problem. There's a couple homework questions along these lines, and it's also a potential concept style question as well, where we're just determining where do these spaces actually live? Is it R2 or R4 for column space? That'd be an important question to resolve. Well, any questions, folks, with getting through this one? Just want to tie down those little containing items. Well, let's try out this next example then. For example 7, we have a large matrix of size 4 by 4, a vector of 4 entries, and we wonder if W is in the column space of A and if it is in the null space of A. Now, this is kind of unusual. Usually, if your matrix is of size 4 by 4, it's not always easy to find a vector that could be in both, but it could happen. But if the size is different, if it's 4 by 2, this is now impossible. If you have an unsquared matrix, there is no one vector that can be in both the column space and in the null space. But squared matrices are special, so we'll see what happens on this one. Very first thing I would do with this is, I'd probably leave this question for last, the column space. There's a trick to get through this one a little bit nicer. But for most problems, the null space is usually the easier question to get through. So let's start with that. So if we want to determine if W is in the null space of A, all we have to do is take A times W and see if it turns into the 0 vector. If it is, we'll say yes, and if not, we'll say it's not in the null space. So we need to work out this multiplication. 10, 0, 1, 1, -8, 2, 1, 1, -2, 2, 6, 0, -2, -2, 0, -2, and multiply this against 2, 2, 0, 2. So that's always the first step in determining if a vector is in the null space. Keep in mind, if we're actually trying to find the null space, generate it as a spanning set, then we would take A, augment it with a zero vector, and go for parametric vector form. That was the example 1 we did right before the break. So now multiplying this all together, let's see what we come out with. So we'll take 10 by 2 for a 20, minus 16, we're at a 4. That'll be plus 0, so still 4. Minus 4 does give us a 0 here. And in an exam question, the hope of hopes is you've got like a 1. If you've got a 1 right in this location, I think I mentioned this before, you could just stop here. A 1 in that spot is enough to say W is not in the null space, because we wouldn't have had the 0 vector. But it has a possibility. It's going to come down to the last 3 entries. So let's multiply these entries. We'll have 0 plus 4, so we're up to 4, plus 0, so still at 4. Then minus 4, we're at a 0 still. Then do it again. We're now at 2, plus 2 for 4, plus 0, so still at 4, plus 0, so we are at 4. And I did notice one problem. That should have been a -1. We're right here. Sorry for that miscopy. That's really easy to do in these kind of problems. You know, I could have just eyeballed it and go here to here, but for some reason it just feels a little bit more precise if I put them right next to each other. That might be a me thing. But let me try again. This will be 2 minus 2, so we're at 0, plus 0, plus 0. So we are still at a 0 here with that correction there. And last entries. This is 2 plus 2, so we're up to 4, plus 0, so still 4. Then minus 4 for 0. Just to make it look more like how we write it, that is the 0 vector. So that says, this implies W is in the null space of A. And it's done. It's really just a matrix computation. Any questions, folks, with that first portion here? Well, I guess that's the second portion we went for first. Okay, I want to mention that this has a way of being a pretty tricky exam question. Sometimes we just kind of forget that that's all you're really meant to do to determine if a vector is in the null space. And sometimes people have approached this question right here, the null space part, by doing this. Actually generating the null space as a span of set of vectors. But even if you did that, you have further work to do to see if the vector in question is inside the spanning set. That could be even more row reductions. So for this question, you don't actually have to calculate the null space like we did in this problem. This one is a homework question and it can be an exam question. It's really just glorified parametric vector form to get to the spanning set. But all we're really doing here is a verification. It's going to be not that much work if you see this problem on the third exam. Any questions at all, folks, at the moment? Okay, now for this portion, there's 2 methods that you might want to take a look at. Let's start with the shortcut on this one. Has anyone observed anything interesting about the matrix here and the vector in question? Could be a lot of interesting things. Looking at these, I mean, column 1's, column 2, column 3, they don't seem to have anything to do with the vector W. And if I think about adding them together, this plus this would be a 2, 2, 0, 2. Those first 2 columns actually add together to generate W. Even weirder, right here, this is the opposite of W. So that's pretty much our shortcut. If there's something like that you can spot, you might not have to do row reduction. In the homework, there is row reduction, so I'm going to show how to do it when it doesn't work out nicely. But this is our go-to method if you observe something interesting. We can start by saying the call space of A is the span of 10, 0, 1, 1, negative 8, 2, negative 1, 1, negative 2, 2, 6, 0, and last, negative 2, negative 2, 0, negative 2. Now I wrote that as a span, but that means this is the set of all linear combinations of those 4 different vectors. Let's name them just so we don't have to copy them once again. Let's call this V1, V2, V3, V4. Now the question is this vector W inside the column space of A? Well, the column space of A is a span, but that means it's the set of every potential linear combination. So let's take 0v1 plus 0v2 plus 0v3 and negative v4. That's a very valid linear combination. These are all ordinary scalars multiplying a vector. So I'm wiping out every single one of these, except the last one. We're multiplying it by -1. That'll turn into, let's put it in this step just to connect the dots. Rescale this, and we have 2, 2, 0, 2. That is the vector W. And so this tells us already W is in the column space of A. That means our work is complete. And this one was really just kind of a freebie, a bit of a trick question. Any questions, folks, on that approach there? Okay, the question I would probably have personally is, does this work every time? And I'd say yes, but finding the right linear combination from scratch could take a lot of creativity, a lot of work. You'd have more luck sometimes with a random matrix and a random vector just doing row reduction to find the right linear combination. So here's the approach I would probably take if I just didn't see any of this in the homework or anything special on an exam question. Let's call this approach 2 or method 2. Let's move down that optional reading a little bit further. Okay, so now for method 2, if we have something that just doesn't look anything special with the columns here and the vector in question, this is what we must say. W is in the column space of A if and only if A times X equals W is consistent. So this turns into now a chapter 1 style problem. All we have to determine is if we have consistency or not. And that means this is just a row reduce to echelon form type of problem. So we would take that matrix A, augment it with the vector W, and just see what happens with that whole thing right there. Well, let's see what does in fact happen. It's a good spot for us to practice some row reduction. First, I'll throw in A, goes 10, 0, 1, 1. I really thought I was done copying those vectors, but one last go. Negative 8, 2, negative 1, 1, negative 2, 2, 6, 0, negative 2, negative 2, 0, 2. Augment this with the vector W, 2, 2, 0, 2. And we just need to reduce this to echelon form to get a conclusion. Well, any questions at the moment, folks, to that stage? Okay, well, let's give this a try. The row reduction, even though we're going for echelon form, I wouldn't like this row 1 right where it's at. That's just not convenient to have a 10 there. So let's start by just flipping row 1 and row 4 to start this one off. So we have row equivalents where row 1 is 1, 1, 0, 2, 2. Row 4 is 10, -8, -2, and 2. And I'm not sure if I would switch these two. I'm not sure if there's a big benefit to that. So I'll just copy them in just as they are. So 0, 2, 2, -2 and 2, and then 1, -1, 6, 0, 0. Been a while since we've done a row reduction. I guess this is a good warm-up after coming back from spring break, so let's run through it. On this first pivot, we need to eliminate these two entries below. So we'll copy in rows 1 and 2 to start. So 1, 1, 0, 2, 2. Then 0. And if it helps, you might decide to just reduce this by dividing by 2. Let's do that ourselves. This is 1, 1, -1, 1. A little bit of a reduction in the complexity by doing that step. Next, multiply row 1 by -1. Add it to the row 3 to get 0. -2, 6, -2, -2. Let me double check that. So multiplying by -1 gives us -2, -2, -2, add to row 3. Now, next operation, multiply row 1 by -10, add to the row below, the fourth row, and we will get a 0. This is -10 minus 8, so -18. No change, -2 goes in. This one is now, oh, these are getting nasty, -20 minus 2, so -22. And this one will be -20 plus 2, so -18. That got kind of nasty out of nowhere, but we're still alive, so let's keep on going through this. To get to echelon form, next thing you have to do is deal with the -2, -18 down below. So again, copy in rows 1 and 2, 1, 1, 0, 2, 2. Then 0, 1, -1. Oh, hang on. 0, 1, 1, and -1, 1. These ones are all looking the same to me. So 1, 1, -1, and 1. There we go. Now the operation can start. We'll multiply by 2, add to the row below. So we will get 0, 0, 8, -4. We're multiplying by 2, so this one will come out as a 0. Now, this is the one that makes me a little bit nervous. We're multiplying by 18, adding to the row below. We'll get 0, 0. This one is multiplied by 18, so -2 for a 16. Hey, those numbers look compatible in a way. Then 18 here, so it's -18, -22, so now we're at -40. Let me know if the numbers seem weird. Then finally, -18 minus 18 looks like a -36. I feel like that one looks like a good one to double check. Let me know if some of the numbers you've spotted are wrong at the moment. Let's see. So we multiply by 18, add below, we got 0, 16, -18 minus 22 does sound like a -40, and -36. Well, it is what it is, so we're on our way to the next step. We have a pivots here, here, and here. Last thing to do is just eliminate that 16. So we're now copying in rows 1, 2, and 3. 1, 1, 0, 2, 2. 0, 1, 1, -1, 1, and 0, 0, 8, -4, 0. And finally, the operation can start. We'll get 2 zeros here, guaranteed. Multiply row 3 by -2, add to the row below to get 0. This will be +8, minus 40, so -32. This will be no change, so -36 here. And this was an augmented matrix, but notice the pivots go here, 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 and here. There is no pivot on the far right column, and that's enough to tell us this is consistent. So let's point to that. We have consistency. And this shows W is in the column space of A. So horrible row reduction on this one. I think there's a harder one on the homework as well. So that might have been the purpose of this problem that I put here. But on a real exam, I'm not going to make it that terrible. I'll probably put it as a shortcut so that if you think in these kinds of terms that the column space is just a span, you might be able to identify if W is in there right away without the row reduction. But that's a good workhorse kind of method, especially in the homework where things are not necessarily rigged nicely. Well, any questions at all, folks, on running through this problem here, the second method? Okay, so that vector W, again, it was unusual. It is in the column space and it is in the null space simultaneously. That could only ever happen if your matrix was squared. Well, we did it, folks. We've concluded the notes on this one. There is optional reading down below if you're interested in more things to deal with null spaces and column spaces. We can retune those definitions to talk about just the linear transformations themselves. But for the next thing we'll take a look at is our section 4.3. I won't go to the 645 today. I just want to take a look at the first initial definition. We'll take a look at the first problem and we'll be in good shape to come back to it on Thursday's class. But any questions at the moment, folks, with what we've done on these notes? Okay, let me save these up. And now here's the portion of the course that we're getting into now at this stage. I think we kind of laid it out in section possibly 1.3. Sounds about right. Vector equations are important. And there it is. So we looked at all these definitions quite a lot: linear combination, spanning, and linear independence. In section 4.1, 4.2, we took another look at spanning, but now we're going to take another look at linear independence. The reason we are redoing all this kind of stuff is the definition for linear independence in chapter 1 was specifically if your vector space looked like this, Rn. But vector spaces are not always like that. They could be a polynomial space, such as Pn. Turns out there are similarities. These are isomorphic spaces, but there's even weirder vector spaces like CAB. That's the set of all continuous functions on a closed set from A to B, and this one is never isomorphic to Rn, meaning everything we did here in linear independence in chapter 1 breaks down on CAB. We need other tools to make this happen. That means we have to go back to the definition of linear independence. We're just going to fully restate it exactly the way we saw it in chapter 1, but sometimes we have to use this definition directly. This will be a problem where we'll use it directly, and then later on we'll see that there is a shortcut to this one, but not to every single problem. Get that down there. Well, to start off, let's just refresh ourselves on linear independence. We get kind of wrapped up in linear dependence, meaning your columns, if you put them in a matrix, would have a pivot in every single column. But again, that definition can break down in certain problems. Instead, we sometimes have to use this definition, the actual vector equation. So linear independence means when we consider the homogeneous equation, we only have the trivial solution, which means all the scalars, we can think of these as x1, x2, and so on, had to be 0. That's the meaning of the trivial solution. That's what linear independence would be. And I did notice a typo right here. This one should have been in bold. Let's go just fix it right here and now. Sorry about that weird omission. I like to put these in bold just to convey that's a 0 as a vector, not as a scalar. So independence means only the trivial solution. And we'll say the set V1 through Vp is linearly dependent if it's not linearly independent. That's a great definition. It's logically sound, but it doesn't give you a lot to work with. So this is what we mean by not linearly independent. There exist scalars C1 through Cp, not all 0, such that that equation still holds. But this is the major portion, not all 0. Just like we said here, linear independence means you have a trivial solution. Linear dependence means you have a non-trivial trivial solution to the same vector equation, which must be homogeneous, meaning equals the zero vector on the right-hand side. So that's our core definition. And now this will be the first time we use it directly for a weird looking vector space. It says, consider the polynomials. P1, that's a degree 2 polynomial. This one is irreducible, so it already has issues. P2, this one can factor, also degree 2. And the question is that set, just two polynomials linearly independent in the space P2? That's the vector space of all polynomials of a degree at most 2. So it includes the constant functions, the linear functions, and every single quadratic. Because it's asking about linear dependence, the very first thing we would do is write down that vector equation. And you could use C1, C2, or X1, X2, really completely up to you. Let's go with X1, X2. We'll take this right here, X1 multiplying P1 of t, plus X2 multiplying P2 of t, and set it equal to the zero vector. So now we're definitely addressing linear independence and dependence once we write down any one of these kinds of equations. The next step is possibly a familiar step, especially if you've taken calculus 2, when you've dealt with what was that horrible technique, partial fraction decomposition. Partial fraction decomposition does intersect with linear algebra, and that's about what we're doing here. In a partial fraction decomposition, what you work with are equating coefficients. We need to do that ourselves to get through this problem. So first thing we'll do is input P1 of t. It's 1 plus t squared, so we'll go x1 times 1 plus t squared. Then x2 multiplies p2, which is a 1 minus t squared. Because we're equating coefficients, we can rewrite this zero vector as 0 plus 0 times t squared. So the reason I didn't put in a 0 times t is because there is no t on the left-hand side whatsoever. There's going to be a constant, the 1 and the 1, that will equate to that constant. Then there'll be a term involving t squared from here to here, which will equate to 0 t squared. So next step, we just distribute. We have x1 times 1 plus x1 times t squared. Then same deal over here, plus x2 minus x2 times t squared equals 0 plus 0 t squared. Finally, next thing to do is start equating those coefficients. This is going to be the constant term, and it goes along with this x1 and that x2. So let's put in x1 plus x2, just to associate them. Next, for the 0 t squared portion, we'll go here and here and just factor out t squared. I'll factor it out to the right to kind of match this format over here. This will give us plus. From here will be a x1. From here, minus x2. T squared. Now equated with 0 plus 0, t squared. We've done pretty much the heavy lifting with this, and now this is the major punchline. This right here has to be equal to 0, and this portion right here has to also be equal to 0. The only way a degree 2 polynomial, or any polynomial, is actually equal is if their coefficients are equal. So that's the idea with equating coefficients. We'll say that this implies immediately x1 plus x2 equals 0, and x1 minus x2 equals 0 as well. So we took a whole entire problem, which is about polynomials, and we made it into a chapter 1 problem. This is the idea with what we're going to do whenever a vector space has a finite dimension. We'll actually always bring it back to chapter 1 and use our chapter 1 methods, because all that stuff is really powerful tools we've been developing. But it doesn't always work. The reason it works is P2 is of dimension 3, but some vector spaces are of infinite dimension. And so this process does break down for those ones. But now that we're back into a chapter 1 process, let me just scribble. We can just directly throw this into an augmented matrix. There'll be 1, 1, 1, negative 1, augmented with a 0 vector. So those are coefficients for x1, coefficients for x2, and that's a really fast row reduction. Honestly, some people might not even row reduce. You can solve just that system of equations right here pretty fast just by adding equations and so on. Let's do it over here just because it's linear algebra. It's a good practice. We'll multiply row 1 by negative 1, add to the row below. So that'll give us 0, negative 2, 0 down below. Then you can divide this row by negative 2. Upon doing that, and scrolling a little bit further, we'll get 0, 1, 0, 1, 1, 0. And now it's pretty much done. Copy in row 2, 0, 1, 0. Multiply it by negative 1. Add to the row above, and we would get 1, 0, 0. Next, we recall that these are coefficients for x1, x2. So this then implies x1 equals 0 and x2 equals 0. In other words, there is only the trivial solution to x1 p1 of t plus x2 p2 of t equaling the 0 vector, the 0 polynomial in p2, that space here. Because there is only the trivial solution, this is what we mean by linear independence above, having, let me highlight that portion there. Only the trivial solution is important. I don't know why I neglected that. So now we get to say that set P1, P2 is linearly independent. So this implies P1, comma P2 is linearly independent. Deserves an exclamation mark because we did it, folks. It's not an easy process working with this definition directly like we did, but this is what the steps would look like. Later on in the upcoming sections, in section 4.5, we are going to really look at what we mean by isomorphisms. We'll create an isomorphism between this space and Rn. It'd be R3 in this example, and we'll be able to sideline most of that algebra and actually pretty much just do what we did in chapter 1. So we will use and abuse isomorphisms down the line, but for the moment, this is the best technique we have for addressing independence in P2. Any questions at all, folks, with running through that example? Okay, I'd say this is probably a good stopping point for us then. When we come back, we'll take a look at the major definition. This is probably one of the more important definitions aside from spanning, because we're about ready to define what we mean by, where is it? A basis. A basis for a vector space is going to be the minimal set that generates every single vector in that vector space. Think of it as a way as defining addresses and coordinates to every single vector that lives there. And all it boils down to are the two definitions that we've been working hard all along, really since the first chapter. A basis is a set of vectors that's linearly independent that also spans the set H that we're interested in. Let me highlight that in green just to tie that together. So that's what we'll return to when we come back on Thursday's class. But any last questions, folks, before we call it a night officially? Okay, well, have a great night, folks, but I'll see you all on Thursday.
Thank you so much. Have a good night.
Thank you.
Thanks.